Hello, this is Darrell Horn, and this is my walkthrough of my final project for Intro to Machine Learning. So let's dive into it, and we'll start with the code. So I have 6 different scripts, one for each of the models we had to train for this final project. I'm only going to go through one of them because they're all incredibly similar. And this is my gradient boosting script. So start by making the pipeline here, and sometimes I tested using a feature select method. Sometimes I tested with using a scaling method, and I tested different PCA options before I piped all of this info to my classifier here, which is gradient boosting. And here I'm listing my different scoring metrics, so accuracy, ROC, AUC, or F1 score. And then I'm also trying some different hyperparameters for the estimator. Okay, so here, after we fit with a grid search using 4 crossfolds, we want to look at how the training session went. So you can look at the different, the best parameters for accuracy, the best parameters for ROC, AUC, or the best parameters for F1. You can even look at those metrics across the different training splits. And after we find our best parameters and best pre-processing steps, we create a final pipeline for the test data. Here, predict probabilities. We look at the accuracy in F1 on the test data. Here, we're generating the confusion matrix. And here is the ROC curves. Here are the precision recall curves. And then we can look at some high and low confidence images and look at some misclassified samples. So these are all misclassified dandelion samples. Okay, and then after that, we have different scripts. This one's for the support vector machine. This is for k-nearest neighbors, multi-layer perceptron. Here's my AdaBoost script, and then here's my stacking script. And they're all very, very similar, so there's no point stepping through those. So let's talk about our results then. Starting with gradient boost. I think my gradient boost did not do very well because I think it was overfitting a little bit, which is evident here from the training accuracy and the test accuracy. It's a pretty significant gap. So I think that's why I didn't perform as well as my other models. You also see that gap here in the F1 score. We can see that it struggled a bit on the tulips, roses, and dandelions classes from figure 2.2 here, the confusion matrix. You can see there, here, and here, it's misclassifying those samples. And we can see from the precision recall curve here in figure 2.4 that it's the rose class as kind of underperforming compared to the other classes. So going on to the support vector machine, this one, what was notable about this is that it had a very good area under the curve scores, both for the ROC and the precision recall curve. It doesn't seem to be overfitting as much. The train and test accuracies are closer together. Same with the F1 scores. So I think this proved to be a very solid model. Still kind of struggling on the Rose class, but that's something that we're going to see across all the models. That's something intrinsic to the data set, it seems. And the Dandelion, Rose, and Tulip classes in figure 3.2, all of the models are going to misclassify some of those. So clearly there are some samples that are very hard to differentiate. All right, on to nearest neighbors. This one, I don't see any evidence of overfitting or underfitting because our train and test accuracies are fairly close, but not too close that we're seeing underfitting happening. Something else that seemed interesting to k-nearest neighbors was that the metrics seem to vary between splits more on this algorithm than other classifiers. We had a standard deviation of 1.96% on the accuracy metrics, which is much higher than any other classifier. I think this is saying that this model may not be able to generalize well to other data based on the pattern it's found. So, onto multi-layer perceptron. I also don't see any evidence of overfitting or underfitting, so this one's performing quite well. The train and test accuracy are fairly close together. Fairly strong area under the curves for ROC and precision recall. This one seemed to struggle a little bit more on the rows samples. We can see from figure 5.4 here, it is kind of a strange bend to their precision recall curve. But overall, it is a pretty performative classifier. All right, on to AdaBoost, which is our first ensemble classifier. What was interesting about this is, although I used multi-layer perceptron as the base estimator for it, because that's what I found was giving the best results, it actually didn't outperform the base multi-layer perceptron classifier. So I believe that is evidence that this classifier is overfitting. Although the F1 and precision recall area under the curves were better than the single model that I mentioned on the previous slide, the accuracy and the ROC AUC were not as good. So on to stacking. I saw that we want to list our reasons for the stacking classifier and justify the decisions we made. So I decided to include the support vector machine, k-nearest neighbors, and multi-layer perceptron in my stacking classifier. I excluded the gradient boosting because it caused the training times to take a really long time, and the performance that it brought to it just did not outweigh that cost. Although SVM, KNN, and MLP, they all had similar performances that I listed earlier. They each misclassified separate samples. So I think they're finding separate patterns in the data, and bringing them all together, they could sort of correct each other on that. So figure 7.1 here, it seems that the support vector machine it misclassified a lot of these white flowers in its data set, whereas MLP, it misclassified some of these samples in figure 7.2, and then KNN seemed to kind of struggle on the sunflower set, interestingly, that's listed here in 7.3. So I think putting these three classifiers together could result in an improved ensemble classifier, which is actually what we see from these metrics here. So we have the best accuracy that we've come across. We have the best F1 and pretty good area under the curve scores. Also, from table 8.1 up in the corner, it's pretty consistent across all the training folds, which, KNN was not. It still kind of struggles on those dandelion, tulip, and rose classes. We see that in figure 8.2 here in the confusion matrix, but it is performing better than any other individual classifier that we mentioned. We're still seeing it struggle on the rose class and a little bit on the daisy class at certain points, but that's something that's intrinsic to the data set, and it's still our strongest classifier that we have yet trained. So, looking at it overall, I think the stacking model shows the best ability to generalize on new data. That's because it has the strongest accuracy here at 91.5% and the best F1 score at 9.15 or 0.915, sorry. These metrics were also fairly consistent, which is what the second number in this table is. This is the standard deviation across the training folds. So we have those to consider. The ROC and precision recall area under the curves were not the strongest for the stacking classifier, but all of them score pretty much the same. So I don't think that's really going to impact things. SVM had the best area under the curve for ROC at 0.99, but stacking isn't far behind at 0.985. So that's why I think stacking is the best model for this problem. Now let's look at some of the samples and what stacking is doing very well. So something I thought might be difficult for the models, but this one was able to do, is to differentiate between both kinds of dandelions. So in the dandelion class, sometimes they look like this yellow flower, and sometimes they can look like these little seeds that blow away in the wind. So, but it was able to consider both into the dandelion class. Also, for the tulips, there were many different kinds of tulips in the data set, but it was able to discern a large amount of them. And here in figure 10.3, a lot of the pictures in the training samples, the flowers weren't really the main focus, which some of the classifiers struggled on those samples. But this classifier was still able to pick it out. You can see that the flowers are these dark things at the bottom, which is not a majority of the photo. And it was still a fairly confident decision here at 0.944. Lastly, some of the images were in black and white, and so it kind of required the classifier to analyze the textures and the patterns within the photo and not just rely on color. So this classifier was able to still pick those out, albeit with a bit lower of a confidence level, but it still classified some of them correctly. On to some confused samples. Figure 11.1 here. These are what I called obvious misclassifications, like they're clearly sunflower samples, but I think stuff in the foreground and the background may have confused the classifier, such as the car or the family here. So maybe there weren't a lot of examples of that in the data set. But it's interesting that it got those wrong because those seem fairly obvious. Another set of samples that I think were the reason for the misclassification are that they're just really difficult samples. This yellow one here, I personally think those do look like dandelions, but they were labeled as daisies within the data set, so it's understandable that the classifier got those wrong. Same with these two down here. Clearly there are some daisies in the photos, but there are things that kind of look like tulips as well, so I don't really fault the classifier for getting that one wrong. Those are very difficult samples. But the last set of misclassified samples that I had in my mind, there were some samples that seemed like they shouldn't be included in the data set at all. Like they didn't really have any flowers, such as this conservatory here, or this bird in the snow, or even this town. I'm not quite sure why those made it in the data set, but the classifier clearly struggled on those. And this one here, I just thought was a very strange pick for a dandelion picture because that's just seems very difficult for the classifier to get, but if it did get it, that would be impressive. But I wouldn't expect it to because it looks so different from all of their samples. So, all right, in summary, I think the stacking classifier has the best ability to generalize to new data. It had the best accuracy in F1 score, and its ROC and precision recall, area under the curve scores, they were strong enough, really. And some reasons that I think the other classifiers didn't do as well. Gradient boosting and aided boost, they both seem to be overfitting on the training data. So those classifiers, I know that's an issue with them, a pretty common issue. KNN didn't seem to it just wasn't strong enough compared to the other classifiers, and it wasn't very consistent across the training folds. And lastly, support vector machine and multi-layer perceptrons, those classifiers, they were pretty strong, but by putting them both into the stacking classifier, they were just outperformed. So, and then I've included the metrics one final time there. So I think that concludes my final project for Intro to Machine Learning, and it concludes this semester, really. So thank you very much. I have learned a lot. I've been able to apply it at my job and in interviews already, and so I'm really appreciative of it. Thank you, Professor. Thank you, TA. And thank you for listening to this walkthrough. Bye.